The Oak Ridge National Laboratory is developing the homogeneous type reactor as one of the 5 technical approaches to economic power in the government's experimental reactor program. In this building, the first circulating fuel homogeneous reactor, known as Homogeneous Reactor Experiment No. 1, was constructed and operated for 2 years. The reactor went critical in April 1952 and first generated electricity in February 1953. The plant included a stack for releasing decayed fission gases, a chemical laboratory, underground storage tanks, a control room, a turbogenerator, and, in a thick shield, the core and other radioactive components. The core was a stainless steel sphere 18 inches in diameter. About 3 pounds of highly enriched uranium in uranyl sulfate solution constituted a critical mass. The core was surrounded by 10 inches of heavy water reflector contained in a thick pear-shaped steel pressure vessel. Both the reflector and the fuel solution were held at about 1,000 pounds per square inch pressure to prevent boiling and to reduce the volume of any gases present. Pressure was applied to the fuel by boiling a portion of the solution in a steam-jacketed vessel called the pressurizer, which also provided surge space. The reflector was pressurized with high-pressure helium gas. The equipment of the reactor installation can be grouped with the pressure vessel into 4 systems: reflector system, fuel system, off-gas system, and steam system. In the reflector system, heavy water could be pumped with a diaphragm-type pump from storage tanks into the pressure vessel and drained back by gravity. During operation, it was circulated through the pressure vessel and a cooler with a canned motor pump. In the fuel system, solution could be pumped from storage tanks into the core and emptied back into the tanks. During operation, about 1 gallon per minute of makeup liquid was pumped into the core to maintain a constant level. This liquid left the core as hydrogen and oxygen, decomposed from the water of the fuel solution, and as an entrained solution, along with a small amount of fission gases. All these gases and the solution passed through an economizer and a throttling valve on the way to the tanks, which were held at atmospheric pressure. A small evaporator generated steam to dilute the gases. The steam and gases rose to a condenser where water vapor was removed, and to a flame recombiner where the hydrogen and oxygen were burned to form water. A small catalytic recombiner accomplished this recombination during low-power operation when the gas flow was insufficient to maintain a flame. Another condenser followed the recombiners to remove heat and recombined water. Cold traps removed remaining traces of water. The small amount of fission gases leaving the coal traps was adsorbed on activated charcoal to decay before being released to the atmosphere. About 20 cubic centimeters of these gases were generated daily when the reactor operated at 1,000 kilowatts of heat. On leaving the charcoal, the gases were mixed with air and released from the stack. Radioactivity at ground level did not exceed 10 to the minus 13th curies per cubic centimeter of air. In the steam system, the fuel solution, pumped from the reactor at 482 degrees Fahrenheit, carried heat to a heat exchanger. Here, steam was generated at 200 pounds per square inch pressure. This steam passed through a time delay drum where it was monitored for radioactivity, then through a quick closing valve before leaving the shield for the turbogenerator. The fuel solution, circulating at 100 gallons per minute, was returned to the core through a tangential inlet pipe so that the solution rotated with sufficient velocity to centrifuge the gases to a vortex in the center of the core, from which they were removed as in this full-scale model used to study the hydrodynamics involved. In this model, air bubbles, simulating fission gases and the radiolytic hydrogen and oxygen, were introduced with the water. They were drawn quickly to the vortex and removed. Particles of paper aided examination of the flow pattern. When dye was introduced, it shut out the light. Then, as the water was gradually removed at the vortex, the sphere cleared up. Further indication of adequate mixing of the circulating liquid. Holes in the sphere permitted introduction of thermocouples, pressure taps, and other instruments. Additional equipment tested included that for removing gases from the vortex, models of the gas let-down system, and the recombiners and condensers. A stainless steel model of the core tank and pressurizer was built and run at full operating temperature and pressure. Much other technological information had to be obtained. Corrosion was one of the first problems attacked, to determine which metals would stand up best in contact with the highly corrosive uranyl sulfate fuel solution. Static corrosion tests in flasks such as these were conducted and are continuing. Ring-shaped samples of stainless steel were suspended from glass rods in the fuel solution. Various gases were bubbled through the liquid to determine the effect of the gases on the corrosion rate. Heat lamps, turned on and off by thermostats, kept the solution at the boiling point. In addition to these tests at atmospheric pressure, high-pressure autoclaves were used to study promising materials at elevated temperatures. With dynamic tests, the laboratories studied the corrosion caused by uranyl sulfate in motion on the stainless steel of test loops. Various bends and shapes in the piping produced turbulence. Reactor temperature and pressure were maintained by a pressurizer which heated part of the solution. Such panels as these controlled operation of the loops. The solution was circulated through the loops by 100-gallon per minute Westinghouse canned motor pumps, identical with those used in the reactor. This type of pump avoids a shaft seal by having its rotor and bearings canned in the liquid line. Samples of different materials were exposed in special sections of pipe which were flange-mounted in the loops. Two types of specimens were used. One was pin-shaped. The ends of the pins were insulated with plastic sleeves to eliminate galvanic coupling, which might complicate interpretation of results. The pins were inserted in a longitudinally split holder so that the fluid could circulate past them at uniform velocity. Thus, many different specimens were tested simultaneously under similar conditions. With the top section in place, clamping bands were slipped over the ends of the holder and crimped. Then the assembled holder was inserted into the pipe from the loop. The other type of specimen was coupon-shaped. They were held in much the same manner as the pins. However, the slot in the holder for the coupons tapered from a wide opening at the inlet to a narrow opening at the outlet. This narrowing of the slot resulted in a velocity gradient along the length of the holder. Thus, with a fixed mass rate of fluid flow, it was possible to evaluate velocity effects upon corrosion. Construction of the reactor began in March 1951. On the right is the support frame for the pressure vessel, and on the left, tanks for the heavy water reflector. The fuel storage tanks were well underground. Parts of the shield were built as columns to support equipment. Space was filled with unmortared blocks. Finned tubes for the emergency cooling system are at the top, and the steam drum is just below them. The pear-shaped pressure vessel was installed in the center of the shield and immediately over the fuel tanks. The fuel pressurizer and control rod housings were mounted above the top flange of the pressure vessel, while the spherical core was hung beneath the flange. The fuel inlet and outlet lines and the dump line are clearly visible. After the equipment on the top flange had been mounted, the assembly was lifted by crane for placement in the pressure vessel, which had already been installed in the shield. Curved control plates of boron carbide, canned in stainless steel, can be seen around the upper half of the core tank. At least 7 feet of high-density concrete surrounded the pressure vessel in the center. 2 feet of the concrete was close around the reactor cell, the rest on the outside of auxiliary equipment. Barium sulfate aggregate raised the concrete density to 3.5. The inner 3 feet of concrete contained 1% boron as colemanite ore for neutron shielding. Only the inner and outer rows of blocks and supporting columns were mortared. This cell contained a canned pump and heat exchanger. The top of the shield was closed with precast concrete blocks 5 feet thick. A conventional turbogenerator, rated at 250 kilowatts of electricity, was installed to utilize the reactor heat. Construction was completed in November 1951. After the reactor went critical, experiments were conducted to measure the effectiveness of various means of control, such as the control plates, negative temperature coefficient, the level of the heavy water reflector, and fuel concentration. Other studies were concerned with operation of the pumps, effects of starting and stopping the reactor, and the amount of radiolytic gas produced. Samples of the radioactive fuel were taken through the top of the shield with a remotely operated manipulator. After the reactor was made critical, the concentration of the fuel was increased until the desired operating temperature was reached. The heat output of the reactor was increased by withdrawing steam. At this point, the reactor proved to be self-regulating. On an increase in the generator load, the turbine governor would open the steam throttle valve, increasing the steam demand and lowering the steam pressure and temperature. The resulting cooling of the uranium solution automatically increased the reactivity in the core, completely compensating for the increase in load. Closing the steam valve lowered the reactor power, since removal of less heat permitted the fuel solution to heat up and overcome the excess reactivity. This self-controlling feature was tested by introducing large excesses of reactivity, either by rapidly cooling the uranium solution or by pumping concentrated fuel into the core. In some tests, the power rose from 30 watts to 11 megawatts in 1 second, returning to 1 megawatt in 1/10 of a second without damaging the equipment. Having served its purpose, Homogeneous Reactor Experiment No. 1 was disassembled early in 1954. The first step was to build a small pool, 15 feet deep, as a convenient place for storing radioactive parts under the shielding of water until they could be examined. The fuel solution was pumped out of the shielded room into its underground storage tanks. Then the components and the piping were partly decontaminated by repeatedly pumping rinse solution through them. The rinse solution was sampled frequently. Activity in the cells, originally several thousand Roentgens per hour, was reduced to 20 to 50 Roentgens per hour. Men with long-handled oxyacetylene torches cut radioactive equipment from the maze of piping to which it was connected, always keeping at a safe distance. Condenser and catalytic recombiner were raised and insulation and broken concrete chipped off. Pocket electroscopes and film badges were worn by the workmen and checked frequently. The equipment was lowered into the pool while a monitor watched the radiation level. The length of time the men could work was limited. An air-operated valve was removed. As a rule, personnel exposures were kept below the general laboratory permissible level of 300 milliroentgens per week. With a long-arm ratchet wrench, men removed the large bolts that held the flange on the radioactive pressure vessel 10 feet below them. They also used an air impact wrench for remote work. A dozen special remote handling tools were devised. With these tools, and by partial decontamination, major repairs were made several times during the operating life of the reactor without overexposing the workers. The flange, with control equipment housings above and core beneath, was removed. The men kept at a safe distance, for this was the most highly radioactive part even after decontamination. 300 Roentgens at 1 foot. In the pool, it was still handled with care to avoid injury that might be confused with damage arising from operation. Looking through a box with a transparent plastic bottom, a man observed disassembly without interference from glare or ripples. He directed an air-operated hacksaw from which bubbles are rising. With the most hazardous radioactive parts out of the way, the masonry was torn down by conventional methods. Even though the men could come in contact with the rubble, its activity was sufficient to require burial at the laboratory's radioactive burial ground. During 2 years of operation at Oak Ridge National Laboratory, Homogeneous Reactor Experiment No. 1 was critical more than 2,000 hours and operated at or above its design heat power for nearly 300 hours. The plant generated 120 kilowatts of electricity from 1,000 kilowatts of heat. It demonstrated that such a reactor can be controlled readily and is self-stabilizing, and it provided valuable information on the behavior of the fuel solution. As the next step in developing homogeneous reactors of this type, the larger Homogeneous Reactor Experiment No. 2 is being constructed in the same building that housed No. 1.